Hi everyone, welcome to the May update for MAIT rocketry. Our early plans to launch this month were unfortunately delayed by pandemics and forest fires. However, those setbacks did not stop us from making a lot of progress, so sit back and enjoy our third monthly update. As stated in last month's update, we needed a new beep beep. The first version didn't have enough planning or precision in the solder joints, so I decided to make a new version. I spent weeks planning the Mark II layout, and it came out much better. Here's the result. Alright, so I've got beep beep Mark I and Mark II right here, and I just wanted to demonstrate some of the differences between the two. You can see on beep beep Mark I, we have all these wires protruding in order to connect it to the charges and the batteries and stuff like that. And while those are useful, they actually make it pretty messy. So on Mark II, we actually have these terminals right here so that we could just plug the wires in and it makes everything a lot cleaner. You could also see on Mark II, we have these wires sticking out right here, and that's actually for the SD card adapter. Since we don't have enough room on the actual breadboard itself, we have to connect it separately with wires. You can also see, looking underneath the flight computers, that Mark II has a lot more planning involved than Mark I. You can see Mark I is pretty messy. Mark II is well thought out and works in straight lines. It just makes it a lot easier to assemble it and a lot easier to fix if something goes wrong. So there you go. We also built a new sled mount for Beep Beep. The old one was hastily thrown together for testing. This new one keeps the wires organized and holds everything firmly in place. It also looks pretty cool. While testing Mark II, I found some bugs with the Beep Beep code that I just couldn't get to the bottom of. It worked as it needed to, but I didn't feel comfortable launching with a program that I didn't fully understand. So, I rewrote the Beep Beep code. By function, it does exactly the same thing. However, this new code saves the altitude data more reliably, and we changed the descent detection procedure to take an average of measurements instead of just one. When launching the Easy i65, I would like to be able to stand an appreciable distance away without laying several hundred feet of wire. For that, the best option was to use the NRF24 radio transceiver module to make a radio launch controller. For extra coding practice, I also used an LCD display to show the launch control status. Writing the transmitter program was definitely our most difficult electronics task thus far. Every time I thought I was done, I'd find a new bug, and then fixing that one would create more bugs, and so on. Once I finally finished debugging everything that I could finally build a casing for the electronics. I made this box out of balsa and plywood, and then painted it to match the motor text box from the last video. Now that I had the launch controller, we needed a receiver to flip the igniter and launch the rocket. I want to be able to always know whether the receiver is connected to the transmitter, so I made this light. Then I tossed together another box and did some testing. So before I show you the testing, I just want to go over real quickly how this works. So first I flip on the power to the receiver, and I know it's on once that light is turned on. And then I flip on the power to the transmitter, and it turns on that green light for a second to show that we're connected and we're ready to go. So I'll arm the system, and once the system is armed, the green light goes on, and I could hit the big red button to begin a 30-second countdown. So right now we could see what time we're at on the display. Every 10 seconds it lets out a little beep to let you know that you're getting closer to the launch. And at any time during this, I could hit either this kill switch or this hold switch to stop the countdown. The difference between them is that the kill switch will stop the receiver for good, and you'll have to restart it before you could use it again. The hold lets you go back to the point in the countdown where you were. So at 0 seconds, it flips the relay and the light goes solid, and after 5 seconds we flip the relay again and we turn the light off. So that's how it works. First we wanted to test the range capabilities of the system. Alright, that's 50 meters. Alright, there's 125 meters. Alright, there's 300 meters. We have exhausted the distance of our test range. And then we wanted to see if it could fire an actual ejection charge. 5, 4, 3, 2, 1, 0, commit. It works like a charm. With the completion of Mark II and the new code update, Beep Beep was ready for some real tests. I brought it outside, put the rocket together with the entire recovery system, and hooked it up to a shop vac. When the vacuum removes air from the electronics bay, the altimeter thinks that the rocket is going up. When the vacuum reaches peak suck, the altimeter will believe that the rocket is at apogee and hopefully eject the parachute. Here's what happened. Alright. Vacuum on. 3, 2, 1. My standard was to complete 3 separate successful tests before deeming Beep Beep flight-worthy, so we got 2 more tests in on separate days. Alright, GoPro's going. Ready? Yep. Vacuum on in 3, 2, 1. And it worked! Nice! Alright, this should be the final test of Beep Beep. Hopefully it works. Okay, vacuum on in 3, 2, 1. It worked! Beep Beep is now a flight-worthy instrument. Throughout the month, motor progress, or lack of it, has become increasingly frustrating. It is the last roadblock for making a fully capable rocket. Just as pandemic shutdowns were ending, Southwest Florida burst into flames, smothering our hopes to finally test the iMotor for the time being. So, I made a dicey decision. You see, in order to deem the iMotor flight-worthy, I not only need a successful Mark I test, but also a test of a second iMotor. This is to prove that the design is reliable and replicable. I decided that instead of sitting idly, waiting for an opportunity to test, I'd design and build the nozzle for Mark II. This allows us to quickly test Mark II if Mark I works, but if Mark I explodes, I will have wasted time and resources on a flawed design. Most of Mark II will be exactly the same as Mark I, such as the burn-web regression, grain size, nozzle size, and casing type. However, Mark I uses a nozzle divergence section that was designed for the H motor. For Mark II, I did some math to optimize the nozzle efficiency and found that the exit diameter should be exactly 1 inch. This is what that looks like in comparison to the Mark I diameter of 5/8 inches. I also used a new centering technique to ensure that the nozzle is pointing as parallel to the length of the casing as possible. With these upgrades, Mark II will be just as reliable as Mark I, with added power and efficiency. I made 2 Mark II nozzles in parallel. The first will be for static test, while the second will hopefully be the one to launch the EZI-65. Building them in parallel ensures that the 2 motors are as similar as possible. One quick note, the reason I chose to retire serial number 2 is because the nozzle was not straight, so we are now on to serial numbers 3 and 4. So, we now have a flight-rated airframe, flight computer, recovery system, launch radio unit, and a launch stand. The only thing needed in order to finally perform a launch is a flight-worthy motor. For next month, you can plan to see a motor test video, and if we are lucky, our first launch report. Thanks for watching this monthly update for Mitchell Atmospheric Instrument Transportation.